You're not muted, right?
No, I'm not.
Okay.
Sorry, let me check.
Yeah, it's okay.
Yeah, I'm not muted. Okay.
Okay, welcome everybody to today's seminar. I'm very sorry for the technical difficulties and starting late. And today I have the pleasure to introduce you to Rodrigo von Marttens. And the title of his talk is Emergent Dark Energy from Backreaction. So, welcome Rodrigo, and please take it away.
Hello, everyone. Thank you very much for being here. First, I'll try to just give a brief introduction of mine. I'm visiting Chile now because I have family here. My father is from Chile, including it's a great pleasure to give this talk here because I was searching that the uncle of my father was a professor just right here in this university, Professor Hernán von Marttens. So it's a very pleasure for me giving this talk here. Okay, I just got a position in University of Bahia in Brazil, uh, which is northwest of Brazil. We had the Cosmos Sul, the last Cosmos Sul there. This is a picture of the Cosmos Sul. Some people from Chile. This is the city of Bahia, and I just would like to say that if one of you go to Brazil and want to visit Bahia, please send me an email. It would be a great pleasure to have you there. It's a very beautiful. How freezing I am here in Santiago. We have a group, a cosmology group there with 6 professors. Those 5 and me, we used to work with observational cosmology, landscape structure, quantum gravity, not me, and machine learning and data analysis there. So we have some students. This is my group, the students I have now. I'm working with dark energy, landscape structure, machine learning. Now starting to work with gravitational waves. This okay. Yeah, so let me start with lambda CDM crisis. And first, what is the lambda CDM? Basically, if we are talking about daytime cosmology, we need two basic ingredients. Theory of gravity in the standard scenario, we use general relativity. Okay, I will not bother you with this basic stuff. And we also need the material content, the energy content of the universe, that in general we have relativistic particles, non-relativistic particles, and the dark energy, which in the standard scenario is cosmological constant. So this is the basic cosmology we can find in books. And then lambda CDM is a successful, or at least used to be a successful description for the universe, because it can compute, for instance, excellent agreement with CMB spectrum, not only temperature, but polarization and cross correlation as well. Now, since DESI results for full shape, it seems we have no more SH tension. It seems. And it seems as well that if we consider just a constant equation of state for the energy, everything works more or less fine, in the sense that we have many different observables, and they have different natures, and they have different systematics, and the lambda CDM can fit everything with the same set of parameters. This is exactly what we want for theory. So this is very nice. However, this works fine for the release one of DESI, and now we have some issues that I will try to show. So, okay, but now, as I'm saying that the lambda CDM crisis, so lambda CDM is facing some big problems. The first one, and which is the one that lasts more, is the H0 tension. So if we have the prediction for H0 from CMB, which is model dependent, which is based on lambda CDM, we have a 6-7 more or less. And if you go to local measurements like shoes that use cepheids, we have more than 5 sigma, we have 73 kilometers per second per megaparsec for H0. We also have some new measurements from Chicago people, and it seems that if we have cepheids, things are more in tension with lambda CDM, but if we use this TRGB or JRGB, they are more in agreement. But still, if we have this measurement from cepheids, we do need to understand why this value is so different from the lambda CDM prediction. So if we compare Planck result with this cepheid measurement, we have more than 5 sigma tension. Okay. Now there is another important tension that has been reported on DESI data release 2 paper, which is this inconsistent between BAO and supernova. And this is very, very important. This is one I found super interesting, because in general, we are used to believe that BAO and supernova were kind of okay. But if we have a CDM model, it seems that the prediction for omega n of BAO and supernova is a bit in tension. For instance, if we use supernovae from DES year 5 and we compare with the prediction of DES, we have 2.9 sigma inconsistency or discrepancy between them. And this is super, super important. It seems are getting messy in the lambda CDM scenario, even considering background data. Including, this is super important for me. If you go to the DESI data release 2 paper, they don't combine BAO and supernova because of this inconsistency. They claim that we cannot use BAO and supernova together in the context of lambda CDM. If you have W3 or W not WA, you can, but in the context of cosmological constant, they don't combine this data together. Okay. And then a third important thing is the preference for a dynamical dark energy. This became super famous now. If we allow equation of state, a time-dependent equation of state for the energy, like CPL parameterization, it seems we are very far from the CDM. Okay. So again, if we use this year 5 supernovae, we have 4.2 sigma discrepancy with lambda CDM, which is very far from what we expect. And actually, one could claim that this might be a fault of the supernova. This might be because of supernovae, since we saw that supernova and BAO is not in agreement. But actually, this is not the case, because even when we not consider supernovae, like in this pink region here, we are out from lambda CDM in more than 2 sigma. If you combine BAO and CMB, lambda CDM is excluded in more than 2 sigma now. So this is not the same thing as the problem before. Okay, this is indeed a different thing. Even if we consider full shape analysis from DESI, this is the data release 1, because data release 2 has not full analysis yet. Things get more or less the same. If you add full shape or not, the constraints remain. Okay, so this is the status of the lambda CDM. It seems it's a good model in some sense still, but we have these issues, and the issues are getting bigger with time as we get more data and more precision. It seems that the problems are getting bigger. Okay, how can we account for these tensions? How can we explain? Okay, the usual suspect is always unknown systematics and bias the measurements. Okay, so for instance, we could have some systematics in local measurements. This is a possibility. Here I have some of options. This first paper from George Statio, a lockdown perspective on Hubble tension. This is a paper I like very much. It's not a published paper, it's just on arXiv. It's a comment on possible systematics of local measurements. It's a very nice paper. Some people are claiming that we have an inconsistency in supernovae. This is also nice. There's this paper, for instance, from Statue as well, that he claimed that the results from DES year 5 is quite different from the Pantheon Plus, so might be an inconsistency between supernovae data, and this might be leading to a discrepancy with lambda CDM. Remember that the big discrepancy with CDM we get using DES year 5 supernovae. Okay, and we might also have some problems in BAO data. There are people mentioning this problem with low Z BAO data, which are more or less LRG data. Here, the solid horizontal line is lambda CDM, so we can see that here we have some data, some missing data somehow. We have this paper from Professor Saponi on possible outliers in BAO data, and yeah, this is the usual suspect. And I would say that the most probable thing. But we also have the challenger, which is a new physics, the new physics. And a possible hint for this new physics is right exactly this discrepancy at low redshift between 0.5 and 1. Here it seems that something is going on, which could also affect redshift 0, for instance, for H0. Okay, so this is the basis for the first part of my presentation. I have this paper, which has been accepted recently in Open Journal of Astrophysics with Leo Gianni, which is a friend from Italy, and Professor Oliver Piatella who has been a professor in my university now, he's in Italy as well. Okay, what is the idea here? In Lambda CDM, matter used to be cold, which means pressureless. Okay, but what if matter is not always cold? It is cold, but recently it's not cold anymore. Okay, that's the point. So this is our hypothesis. Matter was cold in the early universe, and this is important for us because we want to keep CMB as we have now. But recently, around the redshift 1, matter is no more cold. Okay. So we get a toy model, it's just a toy model, which we have a pressureless matter in the past for high redshift, and at some point we have instantaneous transition for a value epsilon over 3 actually, which can be positive or negative. It's a free parameter of the model. Okay. Okay, then the dynamic is super simple. The equation of state for matter is 0 for high redshifts, and from some point on is epsilon over 3, which is we have now two extra free parameters, epsilon and the redshift of the transition. Okay, then energy density of matter is given by this function here, where we have this extra term that depends on some heaviside functions, which is just a step function, okay, to explain our model. Okay. Okay, so we want to test this model just to check if data can allow this kind of transition or not. And to do that, we employ the data with more discrepancy with lambda CDM. So we have used type 1A supernovae from DES year 5, BAO from DES data release 1, because we don't have data release 2 yet. It's not publicly available. And for CMB, here we have a problem. Actually, our model with this instantaneous transition is not well defined in perturbations. I will talk a little bit later. We are now working on a different model with a smooth transition, but in this first paper, we just consider CMB priors, which means that just the position of first peak of CMB, more or less. Okay? So this is the data. We use lambda CDM as a fiducial, and we have this angular distance, and yeah, these observables here. Okay. If
So your observables are just at the background level.
yeah,
Yeah.
yeah, it's
And
just
and in your models, you're just changing the equation of state, like
Yeah.
like this is a
yeah, yeah.
restriction, let's say.
exactly.
And
Okay, we have done this statistical analysis, and we have some conclusions. The first conclusion is regarding the usual parameters, omega m and h naught. We have that h naught shifts down, which is not very good for us. We want a bigger h naught, but this is actually not a real problem for us because we are not using CMB data. I mean, this is just CMB from the first peak. So we think that maybe using full CMB, we can have a more reliable value for H naught. So this is not a big problem for us. And omega m is more or less the same. It shifts slightly up, but it's basically consistent with lambda CDM. However, in the second part, it seems that data finds that a transition is super viable in the sense that we have a redshift of the transition different from 0, which means that data say that a transition is more probable than not. And we have an equation of state different from 0 in more than 2 sigma and negative, which means that it seems that at a given redshift, we need more Dirac energy. It's something like that. Okay. And this is what we find with our model. And then it's interesting to compare with CPL. Here we want to compare with CPL because CPL is a successful model now with this DESI data. And then we can see that we have more or less the same behavior as CPL. Look, if we compare BAO data. So the point is, lambda CDM is problematic with BAO data. The Q-square is super high. CPL can improve essentially BAO data because of this low Z data. And our model works fine as well. For instance, here, this horizontal line, black line, is lambda CDM best fit. And we can see that CPL, which is the blue line, can fit this behavior in the data. And now our model as well. Of course, this peak here is because the transition is instantaneous. Okay, it's not smooth. But here is exactly the best fit for the redshift of transition. But we have more or less the same behavior. So this means that somehow, considering that matter can have a negative equation of state from a given redshift, makes the behavior of Hubble rate and the angular distance more or less as well as in CPL. Okay?
Can you remind us what CPL will
Sorry. Double zero WA. Yeah, just like this.
So your model is you give some pressure to matter, and now the pressure in your feed is negative. It's like that energy.
Yeah, it's like a bit of that energy because it's minus 0.2 more or
But
less.
it's the equation of, I mean, in the equation for H, for the Hubble parameter for Hubble rate,
Yeah,
it's entering as matter. You are replacing the matter for that.
yeah. Then let me show you. Yeah.
With the same omega matter.
Yeah, it will appear this 1 plus Z to epsilon and 1 plus Z over the transition. That will appear this extra term.
So in a way, it's like having less matter and just more the energy.
Yeah, in a sense.
Because if you can split the function equally.
Yeah. Yeah.
So this can be actually seen by the W effective, not when you write in terms of H.
Yeah.
So it's like, putting.
And actually, indeed, this is an interesting point because in the context of general relativity, we have, Einstein's equation constrain the total energy momentum tensor. We cannot have constraints on matter or dark energy. So it's just one thing we can constrain using Hubble rate, for instance. So we can split saying that it's matter or dark energy, and we have more or less the same thing. Okay. Okay, so this is comparison with CPL. We should think now on perturbations, and here.
Question, sorry.
Sorry.
You mentioned before they couldn't use the CMB. What I read was they use CMB as priors only.
Yeah, we use this the LA, omega B, and NS. NS is not used.
Yeah.
But these three as single data in our analysis.
Okay, so you did. You can see that one is the covariance matrix, I guess, no?
Yeah, it's the covariance one. Yeah.
So
This is the value, the fiducial value. This is the covariance one.
with the effective on LA, that's you know you change omega, no?
Yeah. It's basically the position of first peak.
You get it.
Okay. Yeah, we are now thinking on perturbations in a more serious way. Here, however, we have this derivative of the equation of state, which for sure for our model not physical because we have an instantaneous transition. And now we are working, I have a student, Laura, who's working with a model for W to make a smooth transition. And we have some questions to answer, like how fast can be this transition? Because if it's super fast, this blows up. And then we could also understand if we have some signature or multiple spectrum, because it affects delta or in peculiar velocities. And then we want to understand if this transition can give us a signature of something's happening in matter components. We also need to understand what to do with sound speed, with matter sound speed. Should it be adiabatic or I don't know? And then we can get some full semi constraints. This is a work in progress. We have some preliminary results. I mean, background and everything works fine according our previous results. Yeah. However, we still have a question. Okay, but which physics is behind of this transition? This is the great question. And then this, I was chatting with this friend of mine, Leonardo Gianni, and we were trying to think what happens at this redshift, more or less. And one thing we found is that if we get this the collapse of structures, it happens that around redshift 1 we have structures of 10 megaparsec getting at the turnaround. So they are starting to collapse. And also around the 1, we have more or less the same size of structures getting realized. So we thought, what if we have a kind of back reaction of these structures? Indeed, the back reaction has been widely studied, but our point now is, what if we consider back reaction not only from realized structures, but also of structures between turnaround and realization? Structures that are starting to collapse. Let's try to do something to see if we have some back reaction of this kind of structure. Okay, that was our idea. And then we had this paper, has been accepted on physical review letters. I got super happy. Also with Leonardo Gianni and Ryan Camilleri, which is a postdoc, a PhD student from the University of Queensland. And basically, the idea is the following. How do we believe that matter perturbation evolves? So we have in the beginning of the universe, everything is more or less homogeneous and isotropic. So we have very nice initial conditions, and they evolve in a linear way until some time. And after then we have non-linear evolution. And then we form this cosmic web super complex. In this cosmic web, we have clusters, voids, filaments, pancakes, and so on. And it's at large scale, statistically homogeneous and isotropic. This is more or less how we believe that structure form. Okay? And a great part of our understanding in nonlinear stuff comes from simulations, both Newtonian and relativistics. And the point is, can nonlinear matter structure affect global evolution of the universe? Can this structure formation affect the background evolution, the Hubble rate, for instance, the measurement of distances? That's the point. And why we could, and in general, this is the idea of back reaction. And the back reaction idea is just because GR is highly nonlinear, which means that evolution of the average universe is difference of the average of the evolved universe. So let's think that we have the same initial conditions. In general, what cosmology does is the following. We take the average of the universe and evolve the average. Okay? but we could do the opposite. We could evolve the universe and take the average of the universe at the end. And this is different. In a priori is different. Okay? It might be not significant, but it's different. Okay, a priori. Here, that's just the most famous formalism. I'm not bothering you with some mathematics, but the point is, we have this bullshit formalism, which the hypothesis that the usual Friedman-Robertson-Walker dynamics describe the evolution of being observables. And in that sense, if we take a derivative of something, the derivative of the average of something is not the average of the derivative. So this is not commutative. And we have some local expansion rate. And when we do that, as I said, I don't want to bother you with mathematics, but the point is, if we go for the acceleration equation, for instance, if we take the average, it appears an extra term here that comes from this process of averaging later. Okay? And then this extra term is the effect of this back reaction on the background in some sense. Okay, that's the general idea. Okay, and the point is, to be honest, at the present, there seems to be a consensus in literature that cosmological back reaction from realized structures are negligible. This is a kind of consensus. That's why people don't talk much on back reaction. But our point here is, what about non-realized structures? So structures that are between the turnaround and the visualization. If we include this kind of structure, I mean, could we include? Because the point is, including this kind of structure, we can have a bigger stuff, and then it might be the effect would be stronger. And then we propose a new approach for modeling the effect of this kind of structure. It's a super phenomenological approach. I will show you. So here we have the usual cosmology. Our point here is say matter fluid is actually composed by three fluids. One which is physical and two other are not physical. They are effective fluids. So we have one fluid for dust, which is the physical fluid, and we have a fluid, an effective fluid for clusters. So I'm trying to comprise the effect of clusters in a fluid, and one fluid for voids. That's the point. This fluid can exchange energy between them, because dust is collapsing and making clusters, and also getting underdancing, forming voids, so they can exchange energy between them. So if we go to the conservation equations, we have that clusters have a source term here, voids as well, and they go to dust. So at the end, the matter fluid as a whole is a conservative fluid, but each of them have a source term. Okay, and this makes appear an equational state for total matter. Dust is pressureless, okay, because this is the physical fluid. The other two are not pressureless, and the point is, we use the pressure checker. I will show in a second. We use the pressure checker and the similar pressure checker for voids to model equational state for clusters and for voids. That's the point. Okay. So matter is conserved, but we have this equational state here. Okay, so in order to define the background, we need to compute this guy here. Okay.
Sorry, question?
Please.
So define Manus and what classes and Manus in the class and the void is just because you want structure to see the average dynamic.
Yeah, the point is that the sum should be zero.
No, yeah, sure. But I mean, this time means, okay, who gives energy to what? No?
I mean, this is what we expect at the beginning, but it could be, we are not fixing C or V.
Okay.
Depending on the model, it could be negative, and then this could be positive. I mean, we are not fixing at the beginning. But this is what we expect somehow. So that's why we did it like this. Okay. So yeah, just a brief comment. In the pressure check formalism, basically this delta is a Gaussian random field. Then we can define its variation, and we can define the probability of having structure with density contrast given delta x. And then at the end of the day, we can define this fraction of total matter contained in structures with delta bigger than delta x. This is an important quantity. So basically, we can found the matter that are contained into clusters, which is this FPS, which means F pressure. Okay? We have a very similar formalism for voids. Here we have some differences. Basically, the most difference is this, because in general, clusters, we can have clusters inside clusters and then they merge. But here, we cannot have void in a cluster. In that sense, the void disappear. So if we take this into account, it's a work Avisek and this other guy. I will not try to say his name. But they found something very similar, but adapted for voids to compute this fraction of matter that are contained in voids. In that case, things are more complex, and instead of getting f, we have the derivative of f. But okay, we can integrate and have f for a given scale. And basically, the idea, the ansatz for starting our description is that the energy density for clusters is energy density of total matter times the fraction of matter contained in clusters. The same for voids. The energy density of voids is the total matter energy density times the fraction of matter contained in voids. And then the dust will be the difference. Okay? If we start with that, we can begin to build our equation of state. Here, there's something important. We are interested on the effect of nonlinear but non-realized structure. So actually, this F would be the F between turnaround and the visualization. So we have the difference of the pressure in the turnaround and the visualization. The same for voids. I mean, I will define later which is the turnaround and the visualization for voids, but it's more or less the same, okay? Because we know that if we consider only visualized structure, if we consider only FPS of delta C, the result is negligible, and we found that is negligible indeed. But now we are trying to get this bigger structure between turnaround and visualization. For the case of Breschecter, this F is just the error function, and in this case it's more complex, as I showed. Is this numerical integral of the derivative we found. Here it's just to show, the yellow line is the fraction of visualized from the visualized delta, and the green is the fraction from the turnaround. Okay, solid line is redshift 0, dashed line is redshift 0.5. So here is the fraction of structure in terms of the scale of mass in clusters from the turnaround. And here is the same, but from the visualization. What we have is the difference between them, which is the blue line. Okay, is this blue line, the difference. Okay, so this is the total matter, the fraction of matter in structures that are between turnaround and visualization. Okay, this in redshift 0, and this in redshift 0.5. So this is the important quantity to define the energy density. Here is the same for voids. And here we start to think that we might have something similar if we get the before, because we have more voids than clusters. So at the end, when we sum all the fluids, our idea was, okay, clusters will behave like a positive W, and voids will behave like a negative W, which will work like dark energy somehow. And then, since we have more voids, at the end of the day, we have a slightly negative equation of state, recovering more or less what we get before. Okay, so this would be an explanation for that. That was the idea.
I want to for the visualized structure, you're saying that there is no backreaction basically. Is that
For visualize it,
yes?
yeah,
No backreaction, and you're trying to see what happened for these larger structures.
yeah.
So the first thing I thought is because, but for the clusters, my question was, is that because they are more massive and they may have a larger backreaction effect? Because you understand what I mean?
Yeah.
Is that, but then what happened with voice? No.
Yeah. I mean,
So I don't understand why would you expect more backreaction effect from larger that are not yet visualized scales and not for visualized ones? Is because of the mass?
yeah. One of the things is because of the mass, and also because they are more than visualized structure. So the fraction is bigger, and the fraction with bigger mass is bigger. Yeah, that was our starting point.
But then the voice is the mass argument is not valid there because the voice are empty. So
Yeah,
what would be
yeah,
the
but-
reason that larger voice are more important in variation than smaller?
Yeah, they are empty, but not fully empty.
Yeah.
I mean, the under densities are bigger as well. So that was the point. The over densities and the under densities would be bigger, and then because of that, we thought that the effect would be different. I mean, at the beginning, we didn't know, and I will show that there is a strong hypothesis also. And yeah, this is a model, just a model at the end of the day. Okay, so now we need something to compute the equation of state. And basically, when we compute, for instance, the energy density, we have the rest frame energy, and for dust we have only rest frame energy, but for nonlinear stuff we have a internal energy, and that's the point. And for us, here is the critical hypothesis, in my opinion. We identified the internal energy with the curvature energy in the spherical collapse formalism. So basically, the spherical collapse means that the structure they obey an equation just like Friedman equation, but for the structure they evolve like a Friedman-Robertson-Walker universe. And then we have a curvature energy there, just like in Friedman equation. And the point is that we identify this internal energy with the curvature energy. That is the critical point of the model. Okay? And then, yeah, we can, this is the curvature energy, and then we can replace here just to write the things in terms of the scale, and from spherical collapse, this ratio is given by this if it's a cluster, or this if it's a void. And at the end, we have the internal energy as the sum of all internal energies, the clusters of all clusters and all voids. Then we can transform this sum into integrals. One integral for clusters, which is the integral in the scale of the mass function times the curvature energy, here in clusters and here in the turnaround. Okay. Here there's another important point. We have introduced two new parameters because our point is that not all structures between turnaround and visualization are important. Just those who are bigger than a minimum scale. So not if it's too small, it should be negligible as well. So we leave the minimum scale as a free parameter of the model. Okay, so this is the minimum scale that clusters are important for backreaction. This is the minimum scale that voids are important for backreaction. Okay, so yeah, so this is the contribution from the visualization. This is from the turnaround. The same for voids, and for clusters we use the Einstein de Sitter values. So for visualization, 1.68, for turnaround 1.06, and for voids, for the turnaround we found -1. We have used -1, which should be the turnaround, and for visualization we have used -2.81. But the point is, this is not the real data. This is the linear propagation. Okay. Just like in Preshekta, it's not the value, but the linear propagation of the law. Okay. Okay. So then we can do a lot of computation. I will not bother you again with that. We consider that matter is conserved, but then we have this. We have an expression from here to here. There's a lot of calculation. And we can find a model for the equation of state of matter, considering these two extra effective fluids. Okay. At the end of the day, we can combine and we have this. So the matter conservation will be this one, the usual. But actually, when we have this term here, we have this guy here. And this guy here is the integral. So we have to take the derivative of that. And this is actually far from trivial. This is a numerical derivation of a numerical integration. This was super hard to model. Okay, and then we have a final equation for the background. This is the conservation, and we have even though it's phenomenological, it's at least a theoretical based equation of state for matter. Okay? Yeah. So we should go to perturbations as well. And if we have a subhorizon equation, we have this delta equation and theta equation. And we have this extra term because now we have the energy exchange between them. Okay. However, if this Q term should be something like this, if we neglect perturbation of this first term here, we can say that delta Q is equal to Q times delta matter, which kills this guy here, and we have the usual lambda CDM equation for perturbations. Okay? So at the end of the day, we have these two equations to solve, the background energy conservation and the perturbation equations. Okay? The point here is that we have these two equations and they are coupled. They are not independent anymore, as in lambda CDM. Lambda CDM background is independent of perturbation. We can solve background independently of perturbations. Now we can't, because here we have the Preshekta formalism, so we have sigma 8 in the middle. So we have to solve this as a coupled set of equations. Okay? Yeah. So now no mathematics anymore, just some results to finish. So this is what we have at the end of the day. Some of the results, let's see, for instance, the solid green line. This means that our mean, the minimum scale for clusters is 50. This is the same of saying that we are not considering clusters effect. Because if the minimum is 50 megaparsec, there's no such there's no considerable number of structures bigger than 50 megaparsec. So basically, in solid green line is the result for voids, considering only voids, considering the minimum scale as 10 megaparsec. And then we have something as expected. So equation of state is 0 in the past, and here close to 1, it goes a bit negative. This is the effect of voids. And for clusters, we can see the solid yellow line. So we put the minimum scale for voids, 50 in voids, which means that we are neglecting the effect of voids in practice. And we consider the minimum scale 5 for clusters. And what we have is that it's a bit positive nowadays. Okay, so we got more or less what we had before, but in a more physical, even though it's phenomenological, in a more physical based way. Okay?
And why the smaller voids will give this?
The difference is because we have more voids than clusters. So for in order to have the same
The green dash line.
here we are changing the minimum scale. So we are saying that more voids are important. So the effect begins earlier and it's stronger.
I think it's your point.
Yeah, this is something we had an explanation. Sorry, I don't remember exactly. We have an explanation for that in the paper, but I forgot. Sorry.
But it will give you, because from version 1 on, it will give you a positive, like it's not the
Yeah.
dark energy behavior.
Yeah, but the point is, the idea is that the data would constrain the minimum scale. So probably the minimum scale for voids could not be 5, but from of the order of 10. And that is what we will constrain with data. Because we know we need something like this. So if we do the statistical analysis with the model to constrain, because those are our free parameters now. So we can constrain them and possibly the data will constrain in a value closer to 10. Okay. Okay, if we mix them, now both are important. We have both of the same order. We can have some mixed stuff as well. Okay, they are free parameters, and what we should do is statistical analysis to try to constrain them. Okay, here we had an issue. The code, since it's super complex, is super slow. So we could not make a full statistical analysis. So what we've done is the following. We fix lambda CDM as the Planck best fit, and we leave only the 2 scales as free parameters. And we would like to see if we could find something that could explain all different data. And what we have is that we do find something that can fit supernovae in blue, BAO DESI data release 1, it's wrong here, and F sigma 8 with the same value for the scales of voids and clusters. Okay? And
But this supernovae you have by model, no? Have you?
yeah. I mean, indeed, the convergence was hard. And but still, we need the future work would be leaving all parameters free and trying to have a full analysis.
But the integration of the equation, you said that background and perturbations are coupled. Is
Yeah,
that what you said?
yeah,
You're integrating like all together,
yeah.
you're using. What equations are you integrating? The delta matter?
The delta matter in the conservation equation, the background conservation equation. Because they are coupled now. The equation for a whole.
But, okay, but the rest of the species, you're not integrating, you're not
Yeah.
using count or.
No. This is just a thing we've done. Because the point, we could try to modify CAM or class. However, the modification would be super strong because in class or CAM, perturbation and background, they are independent. We should make them connect and
Yeah,
make
but
them
I don't
coupled.
see how you connect the evolution of all the species together here, you're not doing that.
No, I'm not doing. We are just considering matter in this matter fluid total and cosmological constant. Okay, just to finish, basically the solid line is our model, and as expected, we have more or less the same behavior, and we can get all the DESI data as expected. So we improve the statistics with DESI data with our model. And actually, that was a bonus. We made a prediction. Here is the minimum scale for clusters, and this is the minimum scale for voids. And then we did this grid just to see if we start with H naught, just like in best fit in CMB, what would be the final value, what would be the H naught, indeed, the Hubble rate at Z equal to 0. And we found that there's a region here that gives exactly 74. This is an extra. And which values are these? This is a minimum scale of more or less 5 for voids. And we must have big scales for clusters. So at the end, clusters should not affect, and we have small 5 megaparsec for voids. With this combination, we recover H naught equal to 74. More or less in this region as well, we can make sigma 8 a bit less than lambda CDM value. So this was super nice when we found. So we could explain the DESI result, H naught and sigma 8 in the same direction. Okay? Yeah. So let me go to the conclusions. So we found that current data favor this transition in matter equation state. We proposed this model, this phenomenological model, claiming that could be a backreaction of the structures between turnaround and visualization. Our approach seems to be promising. We need to study it more, do the complete statistical analysis and so on, as I say here. And here is the more critical point for me. Okay, this is a model, and at the end, this is just the equation of state that could be, we could understand if this backreaction of these structures between turnaround and visualization is really important in a more fundamental way. We are trying to understand, I'm not the simulation guy, but we are trying to understand the relativistic simulations to see if we can do something. And yeah, if you have something in mind, send me a message. I will be super happy to collaborate. Okay, thank you.
Thank you, Rodrigo, for the very nice talk. Are there any questions?
Yeah, I have a question. Thanks for the presentation. You said that those new parameters for the analysis were free.
Yeah.
Yeah, but I was wondering if those parameters were fixed for the vision of the retina, or they may be dynamic.
No, I mean, they are free. They are free in the analysis, but no, the parameters are the minimum scale that is important for back reaction. Of course, this changed the redshift because the redshift that a given scale reach the turnaround is different. So there is this here. So for instance, this is the redshift of turnaround in terms of the scale at the turnaround. So basically, if you change the scale, you are changing the redshift that the structure end reaches the turnaround. So somehow it will affect where the transition occurs somehow. So it's more or less inside of this parameter. This parameter can control more or less where the deviation will be important. So for instance, if we see this like this, for example, yeah, this is this is the scale, for instance. Let's see the green line, solid line in redshift 0. In redshift 0, if the minimum scale is 10, so this will be the fraction there. However, if the minimum scale is 77.5, so this part of this fraction will be important at the end. So not sure if I could explain.
Yeah,
The point is, depending on the scale, is the redshift where the structures reaches turnaround, and then the transition will start to happen. Okay.
Thank you. Any questions?
So I have two questions.
No.
I know, okay.
Me? Okay. In the one of the last plots that you showed where the value for H naught was increased to 74, I noticed that the scale for the voids is 5,
Yeah.
and it's kind of the same scale where Claudia was
Yeah,
asking the
that's
question
correct.
where the equation state parameter became positive. I'm not sure if I'm correct with that, but one of the last plots
Yeah.
you showed this one.
Yeah.
It's kind of the same scale, so
Yeah.
could it be an effect of that, or?
Possibly. That's sad. I didn't realize that.
Yeah.
Yeah, I mean, we are working on the because the point is lambda CDM is fixed, so this limits our conversation. If we because these parameters they should have degeneracies with lambda CDM parameters. So I mean, this is just honestly speaking, just to sell the paper. But I mean, in order to have a strong conclusion, we should leave all parameters free and understand the correlations of them.
Exactly.
Yeah, I mean, we found this figure super beautiful. And
Don't put the
sorry.
other one.
So,
Your second.
okay, because I think it's more related to the phenomenology of having a equation state parameter for matter, because using statistical mechanics is how we find that color matter or non-relativistic particles, the pressure that they have is exponentially suppressed by mass. And I kind of see the point for voids, since it's like nothing that they could contribute with this, but I don't see the same for clusters. I don't know if you have some sort of intuition for that, or it's probably that
Yeah, no.
these tools that are in like thermodynamical equilibrium that are no longer valid. So I don't know.
Yeah, that's the good question. Yeah, I mean, we don't have a microphysics. We are just applying this pressure, but we don't have a microphysics. So indeed, this is something that we should, we must, I would say, try to understand better if we want to make it this as a line of research indeed. I mean, this is just the first paper, and yeah, this is the good question. I mean, as I said, the critical point was this identification with the curvature energy, but in principle, there's no reason to do that. This velocity, I mean, yeah, this microphysics should be better understood.
My last question, which is quite short, basically, but when you integrate the equations from where do you set the initial condition and how? From what one are you starting to?
We leave the initial conditions at redshift 20 more or less,
Okay.
because we saw that for all values, they go to 0 in redshift 10. So basically we compute class from the beginning and we go with class until redshift 20. From redshift 20, we just glue this resolution. That's what we know.
Okay, no further questions. Thank you, Rodrigo, again for everyone.